what I want to discuss is ensemble of structure of the matrices, how we characterize them via axioms and the relation with cyclic dominants, which I will tell you what we call cyclic cumulants. Then I will discuss the relation between those cyclic cumulants and free probability. And then maybe the new things compared to the standard theory of random matrices, I will explain how these set of ensembles are stable under nonlinear transformation. And there are different kinds of nonlinear transformation that you can do. And then maybe if I have time as an application, I will look at algorithm which able to compute the spectrum not only of the matrices but of subblocks of the matrices. Okay. But before maybe we have to recall the standard ensembles that you know probably better than me. So for example, there is a Wigner ensemble. The one I will discuss more is one related to R orbits, which we already discussed in the previous lecture. Of course, there will be this set of ensembles that we try to, on the framework that we try to develop, emerge from QSET, studying QSET. So there will be some overlap with this lecture, but we have tried to extract the property which were useful to make the new framework. So R orbits means that you look at the matrices N, which are that in the orbit of some diagonal matrix. So U belongs to SUN, okay? And D is diagonal, N by N. Okay, so there have been many studies about that, and actually, about the relation between free probability, which was initially defined in the non-commutative settings, and random matrices was done by École using these kind of matrices. And so, what this measure? So all these set of ensembles are Lorraine invariance. The law is the Lorraine invariance. And one consequence of that is that if you look at the relation of moments of the matrices with different indices, so these correlation functions are actually independent of the indices up to their topology. So it's only a topological correlation function. These are topological. Meaning that they depend whether some of the indices coincide. There is coincidences between the indices, but not of the explicit value of the indices. So it's like a topological correlation function in field theory. So that's one property. The button is missing. Another property that you can compute for so that's one property. So for R, one property that if you look at the expectation value of cycles, you understand already from previous lecture on QSET that we were interested in cycles. So you look at that, MI1, I2, and IT, I1. So it means that the indices from a cycle. I1, I2. this scale like, so if they are all distinct, all different, this scale like 1 over n the p minus 1, and with the coefficient which is independent of the indices because it's topological. And this coefficient, as I said it already last time, is the free cumulant of the diagonal matrices. So you assume that there is diagonal matrices. So we assume that D has the spectral measure at large measure. Mu D in the limit and to infinity. So mu D the spectral measure of the D distribution of its eigenvalue normalized to 1. So this defines a quality measure. And this coefficient here is a free cumulant. So there is sub-limit term here. So this, maybe you know it better than me, it's well known. Maybe the first occurrence was in a paper by Dixon Zuber long ago, Dixon Zuber, before free cumulant was known. The theory of free probability was known. So that's kind of property we want to generalize, not that one. And this property is linked to the last one, is linked to the fact that if you look at the relative function of the matrices, where A is just n by n matrix, this is, if you take it as finite form, this is like exponential sum over p bigger than 1 over p, makes a to the p. N is that. So from that, you can deduce that equivalent. Okay. Okay. So what we want to generalize is the
rank remains finite when n goes to infinity.
Excuse me?
The rank has to remain finite when n goes to infinity.
So you know, as I said last time, this is given by the Dixon Zuber integral. There is all this expansion you can do on it. So what we want to generalize is this property. So we want to break this property. So we look at generalization. Maybe a number one. So, but not for structure matrices. What we mean structure is that the law will not be permutation invariant. So in particular, the fact that this is topological is not only due to the UN invariant, it's due to the permutation invariant. So then you permute the indices with besoin dépend des indices.
The connection is
Yeah.
You're going to show it?
Yeah, no.
No?
You can see it in one of our analyses. You take A, the cyclic permutation. Cyclic permutation because the first rate which will be non-vanishing will be cyclic permutation for the R. Q here. Q of 1 P. So the first trace which will appear here, so Q equal P, then you expand on it. So what we are dealing with Q set, but you can try to abstract, is a generalization where you have social matrices, which means that rho is not permutation invariant. Which means that there is not a democracy, but there is not equivalent between all the entries in the matrices. So it means that the one is left up corner, upward corner has not the same distribution as the one in the bottom left corner. Whatever, there is correlation. So there is not these things. And then we want to have more or less the same property. Okay, this is what we have. The plus some, at least some behavior with n. As n was switching. And that will be summarized a set of axioms, which will be property defining the ensemble. I don't know if axiom is a good word or too big, so we consider axiom. Oh, it's a ensemble. One, so we have a matrix, we have a law, P, so n by n, the law, and we take goes to infinity. And we impose, so the first property we impose is local U1 invariant. So it means that we don't want the UN invariance, we just keep the U1. Local means that it's actually U1 to the n, which is included into UN. And we demand that the law is invariant under this U1, okay? Which means that M in law is some distribution of M back for U1 to the N, which is the same thing as M and J, law. Okay, that we demand that. But this does not include the permutation invariance. Then we demand that the cyclic cumulants n and n to the 1, which means, as I said, m I1, I2, n I2, I1. This is from this cycle. So you will order P. So they behave like 1 over n to the P minus 1. But now, coefficient which is here may depend on the position of the indices. It's a function of order P of x1, xp, plus the subleading, 1 plus n, in the group where xk k over n fixed. Okay. So let's discuss in set, we know the function. Okay. For distribution, this for when you have the UN invariant, this is independent of x, and for the R orbit, just a free cumulant. So we just extended by saying that now everything can depend on the position of the indices. Three, so cumulants are continuous. At question point. Which means that we can look at loops, or we can pinch the loops. On 4, so yeah, make a comment on 4. So initially, So we have written a paper with Ludwig who was my student, now he's doing neuroscience. Initially, in the paper, we have written a paper where we extract what we knew about from QSAT. We had an axiom which was just about factorization of loops, expectation value. Now we think we should promote this action to a bigger one. It means that scaling of disconnected. So we are going to write a small addition to the paper. Of expectation. It means that you take the moment you take air cycles, which means it's kind of things, air times this. So instead, the cycles should be disjoint. Okay, so it means that the indices in first cycles differ from the indices in the second cycles, and so on. So there is R cycles with N altogether N matrices, N matrices N. Okay, so that's the cumulant of order N, because the cumulant is with respect to variable N entries. This should scale like N minus R minus N. So this is what occurs in a R measure, and we realize that we should do that also because there is a recent paper by Spicer with whom we discuss, and in different contexts he also imposes that. So for example, if R equal 1, which is that one, you find 1 minus N, which is the same thing here with P. Okay. So that's the set of actions. So then from that, we try to see what it gives. So maybe some comments. So in which order I wanted to make comments? Yeah, so okay, so I already defined the axiom is that was order NP. So the data the GP of X1, which is to then define limit N minus 1 of N by 1 minus 1. Maybe that's one. Second is that there's a graphical notation I already mentioned that I will Mij is given by the age from I to J. So this is the expectation value of N P minus 1. Look. And this one corresponds to with this graphical notation. What we know that the cumulant of N with N loops that will be N. And there is comma with the spectrum. And while we
This rule also works for diagonal elements.
yeah, so what do you mean diagonal element? If you have
J.
diagonal elements will be a loop of single loops. Okay. So for example, if I take C2 of M I M J J, I different from J, which is C2 of I j, that will be n 2 minus 2 minus 2 and minus 2, not minus 1. Which is different than if I take C2 of Mij and Ji, C2 of Ij, that's n 2 minus 1 minus n, so which is example of minus 2, which is n minus 1. Okay.
I equals J, the last formula is still works.
I equal J, this is what I meant by continuous. You can clean J. That will be exactly the same thing, and the value for the cumulants, not for the expectation value. Because expectation value is factor. This formula implies that expectation value in a cumulant of product of cycle factorize at leading order. So for one consequence of that, implies that the trace of L is self-averaging. Which means that the expectation value of exponential z trace of L is the same thing that z expectation value of trace of L. Okay. For product, you can check. Let us look for product. This means that only the first cumulant contributes. The second, let's say, all the cumulant of trace of N are subleading in N. So how to prove that? So I will just do the first two cumulants. So the first one, C1 of trace of N, that sum over I. Okay. So that's for the N integral of x, d1 of x. Okay, N because the sum then becomes the integral. That. Okay. So for the one, if I look at the second one, trace of N, that's sum over I, j of the cumulant of I, j. Then there is two contributions. I different from j, C2 I, j, plus sum over I of the cumulant of I. Okay. So this one is for the n minus 2. This one is for the n minus 1. But there is only one sum, so that's factor n. There is two sums, that's a factor n squared. So this is O of 1. It doesn't contribute. So for just to anticipate, since we will have stability under nonlinear transformation, then this means that the trace of these nonlinear transform matrices will also be self-averaging.
Yes. Is it crucial in your 4 point that you have this particular scaling, or do you just ask that there's
so that's stronger than just that, yes. But I think this is crucial to have the stability. Also, we are working on the proof of the stability.
You think that will require it? Perhaps.
But this is what you have for R. Okay. So any questions?
So you're working on the proof of what?
So this action we understand with logic, we understand the recently that we have to add it. Because we need this self-averaging property to show this almost show classicality of transport property. So in the original paper, we just demand factorization of the loop, and that's stronger. And we are checking or giving argument to mathematicians that the nonlinear transformation I'm going to mention preserve all these actions including that one. Maybe I will keep the action from that. I don't know. Depending if you remember the action or not. But you could. Ouais, erase it. So now I want to do the. So you see these actions are show that there is a main role for how to say it. So this one is I forget. So trace of n, trace of n is not is self-averaging. But if you look for any matrix element of n, this one is not self-averaging. And there is a large deviation function. Which we know that you can express in terms of the data, which are the loop experiment. So the main formula is the one I want, what I want to see. So the data is here, and that's cumulant of the loop, and which is the same thing as the expectation value of the loop if one indices all I and if they are not, then these expectation values there will be something linked to the fact that you have coincidence of indices. And the main thing I want to discuss now is the formula, magic or nice formula, which I already mentioned, I think. That if you look at you take D1 dp diagonal matrices with d I is some function di related to I over n, so gk for any k. So you have k function smooth on 0, 1, okay, and you compute the limit n goes to infinity of the expectation value of the normalized price of cyclic product MDP. Okay. So we introduce the matrix just to mark the point in the and this is the expectation value. It's not the cumulant, so that would be coincidental. So by this will be finite due to the scaling. It's linear in D, so it will be product over k dxk d of dk of xk. Maybe it's not a good name, D. Okay. And then there is some function by linearity. There is some function t of order p of xy, xp. And the formula maybe I mentioned, I'm sure I mentioned last time, that there is an explicit formula of t as a function of the data. T of x1 xp is the sum of p, the non-constant partition of g p of x delta p star of x. So I have to explain a few things. So that's non-constant partition function. Function partition. And that's called the last time Clever dual. Which means that so here to point x here, so t corresponds by linearity to the so t is up to a scaling np minus 1. Expectation value of something between E1, E2, which are x I k, which is integer part of that. Okay, so this non-crossing partition are the partition of the order number n1 complete. To define non-crossing partition function, you have to fix an order. So you have the points here, x1, x2, e. So this one is on x3, xt. So the partition P is on the edge. So a non-crossing partition is that I will draw the same thing as last time. I draw the blocks. So say this is a. Okay. So it means that I have. Okay. Here I have 1, 2, 3, 4, 5, 6, 7, 8. P equal 8. So here, this is a partition which is not crossing because the green line do not cross. And when I draw a line, the edges, because this is the partition of the edges, when the edges belong to the same block of the partition. So here it's a partition with 3 blocks, one made of the 2 edges here, one made with the 3 edges here, another made with the 3 edges here. Okay, so that's a part. Given a non-crossing partition, we define the traversed dual by star, which will be a non-crossing partition on the points, on the vertices. And this is just mean by squeezing it here. This one is a singlet, this one is a singlet, singlet. Okay, so you just squeeze in between. Okay, and of course it's a non-crossing partition for the of the vertices, and there is a duality. If I was giving first the red non-crossing partition, I will have construct the green one. Okay, 1-to-1 correspond. Right here.
So what's the meaning of this G pi x?
Then that's what I will define them. So partition is made of blocks. So G pi of x is the product of all the blocks which belong to pi of G p of x. So what does it mean here? Here it says that there was 3 blocks. So there will be these blocks of our 2. We will have G2. G2 depend on 2 points, and the points are the one associated to the blocks. Okay. And delta pi, delta p star x is delta function including equality on x, which is x, which belong to the same blocks. Here I have delta. That's x3, x4, 5. I said 8 before, no? I never know how to count. There's only 7. No? X6, X7. Okay. So here there is a delta function x2 should be equal to x4, and x6 should be equal to x4. Okay. So I don't know if I will prove that.
I'm still confused. So what is this G pi again? I mean, for this example.
So I will do. Let me do this one delta function. I told you it's the one.
The G pi for this example.
which is the same thing as x4, which is the same thing as x6, which is the same thing as x6. No, well, x4, which is x2, x5, x. Okay. You follow the loop. You have loop thing. Okay.
Yeah, but the loop goes to the edge, right? So
Yeah.
which X you put?
But this is one edge, this is one
Yes.
here. So you follow it. Now you move here because of the delta function. You are here. You are here. So this one. So this one, this corresponds now to a loop which is made of x1, x2, x2 is here, x5, to x5 I go to x6, which is x1. So this is okay. So this gives me this factor here. Okay. This one is start at x2. I go to x3. That's why it was 3 here. Here was 6. X2. Okay. Then, so I am here. Then x2. X3. And then x3 to x4, but we it's the same thing as x2. And then the delta function are the one in green. So delta pi star, delta x2 minus x3, x4, delta x1 minus x6. Okay, it's explicit from the door. So for take two matrices, trace and d1 and d2. So that's some of the same computation as before, the expectation of that. So it will be, so I pick an indices, which is I here, J, K. So I have D1 at K, D2 at K, computation value of M, I, J, J, N, like D2, and we get okay, and then okay. And then I do the same trick as before. I decompose. Now, this one I can write it as cumulant of order 2 Mij, Mji, plus cumulant Mij, C1 Mgi. Okay? Expectation value is the sum of the cumulant of them. Okay? So this one. So this one is a loop, C2 of the loop, Ij plus C1. But here, I have to close the loop, otherwise I get 0. So I have a delta function here. So then I have delta Ij, C1. Okay? So I do. I have sum over Ij, C1, J, T, I. Of, so now it becomes x2. Let's say J. Let's say it was G over N as a function. Okay. G over N, G over N. This one is N minus 2, G2, I over N, J over N. That's for I, for function. It's for I of J continuous. And sum over I, because there is only one sum, and then there is a sum factor. D1J I over N square the coefficient here, which are T, G1, so there is no factor N, G2, I, N. Okay? And this becomes N, so integral dx, dy, d1 x, d2 x, d2 x, y plus delta x minus y, d1 x, d2 x, which is my formula, because here I have 2 points, okay, and I had two. That was 1 x1. We call it x and y, x and y. There is either the partition where I glue the two one, and this corresponds to G2, or there is one where there is two singlets, but then there is a color dual is the one where I link. Okay. And what I showed you last time is that only when you do this sum, only non-crossing partition appears. So I will, can I erase that? So to prove it, I'm going to do the proof. You start with the loop. So I will do the proof I already mentioned last time for p equals 4. So you write it as the sum over cumulants. And the sum over cumulants is the sum over partitions. So this is sum. So my variables are the edges. These are the random variables. So I will write it as a sum over the cumulant associated to the partition. So that's over all the partition for the P of the cumulant of my edges associated to the partition. The cumulant of the partition is the product of the cumulant associated to the block. That's a standard formula. It comes from the log. So then I expand here, as I said last time. There is meaning. Ouais, donc de partition. And then you have to sum over the indices and so on. So there is the one where you do, that's the full partition. That's the one where you do only 3. And the cyclic permutation. There is the one where you have 2. With this one. And there is a single. Okay. What's the sum? And what this theorem claims is that all the crossing ones are subleading. All these ones will scale, if you sum over the indices to reproduce the trace, they will scale like n, exactly like that. But this one will be subleading. Okay? Just two. So this one, subleading. So this is a kind of big theorem. Not in terms of pairings. Okay. So that's the main formula from which you can prove everything. Yeah, okay. So the two claims now is that I will stop. Then I will describe it. So claim 1. M belongs to such is a sample of such ensemble. And P of M is also for any polynomial P. So it means that you can look at if you consider M, you can consider a new matrix which I will call P, which is P of M, say M squared. Okay. Then it will satisfy the same two actions. So we have to prove the last one, but I think we're close to the proof. And there is an explicit new with explicit. New cyclic dominant. Means that if you have an explicit formula for G P, P is the polynomial, P of M, for the N in terms of G N, actually M less than N of N. Okay? And you can check the focal point square. And that's useful. So if you prove for the last one, as I said, an application to that P of space of P of N is self-averaging. And then there is a claim 2. So we take again M for M central torsion symbol. Let's matrix Y with entries Y I J. So we are going to do a nonlinear transformation, but a different nonlinear transformation for each entries. And the one before is that it's Mij, Fij, N, I think. Didn't forget. Square. Is it the N or N square? I think it's N. Where Fij are at least pas smooth quoi, any admits any series. C'est théorique, ça existe. We belong to, how you call it, T of Q, no? But in terms of the Taylor expansion. So it means that you, okay, and since it works for any, you can change the depending F12 can be different from N 2 millions and absolutely, I don't know.
But so how does Fij depend on ING?
As you want.
Constraint.
As you want.
But how do you take the larger limit then?
Yeah.
This way? Ah, it's independent of N.
What do you mean it depends
What do you
on
mean?
ING depend on it?
Ah, well, is there a limit of Fij of X?
Smooth.
We have a function, yeah, of course.
Okay. Depends.
We have X, Y, U,
Mm.
given smooth Taylor expansion, Fij is F, so X equal Y over N, F,
And I.
absolute value of where is
I
it?
over-
Fij, no, I over N. How much? Okay.
Yeah.
Yeah, so we don't care about so you can, and that was suggested again discussing with Spicer during sometimes the year before. I had to stay home during 3 months because I had an operation. So I was watching a video by Spicer about application of random matrices to machine learning. And then I was discussing with him, and then. That's the kind of transformation you want to do in machine learning because you have a big network and you do nonlinear transformations and the step functions. So again, we have to check the action
Claim that Y satisfies the same stuff.
Huh?
The claim is
Then Y belongs to.
Is it in the same class?
Is some, yeah, of some kind.
Yeah, but then my question is, your F, I should think of it as decaying or something, so the diagonal entries of.
And we know exactly, just finish, is known. Zero.
So, the diagonal entries of Y are zero then? Because, I mean, then you imagine that MII is, order one, so that means that the F would be
No.
very big.
No?
If I equals J, I think
We
of,
look at the loop.
but MII squared is of order one, no?
Yeah, but in the limit,
So you're taking F,
we look at the loop here. MII, what I do. Maybe it starts with one.
F in U or in U over N?
Huh?
F is in U or in U over N?
How it just works. I forget the brain.
F is just a linear function and this becomes a polynomial.
No,
No, I mean, it's what.
no, it's because entry by entry. F, no, it was working. Okay, yes.
yeah.
I think we had a proof. I mean, okay. So if the proof is correct, for mathematician, it's a way to generate, you alternate between the two and to generate many ensembles with structure matrices. So I think we have a proof for the first three, but the fourth we don't, because we actually.
In this way, can you make JY, can you make it topological? Can you
To change. I know.
then you could question,
No,
like,
because-
is this ensemble just a transformation of the topological?
Again, if the proof is very correct, it's simple. So you to find this one, no, you can so GY is the same as the original one, but you have to dress by only the loop by something which is very simple. So you just dress by something which depends on F. So it's I think not possible. And one thing that we know what these things is the spectrum of subblocks. So the question is, you have a matrices N, and you look at subblocks. So you extract the blocks. And even maybe you can extract different blocks and you glue them together. Okay. But that's it. So that's it. And you want to know the spectrum of these subblocks. Blocks is extensive, so this is of size N. And this is of size Ln. Okay, we say. And then you have, let me call that MH. And radius.
Wait, can you just, what is the spectrum of the whole matrix? Is G1 of X?
No,
What is,
but that would be no, it's complicated. So you want to know the spectrum of N. Okay. And in particular, if L equal 1, you have the spectrum of N. For example, I don't know if you, so for Wigner, you know the answer, it's good, it's so that's easy, this is a semi-second law because Gaussian. And for R, you know what it is? For R orbit? I didn't know before. So this is, so you have a nu, which is mu d of N. This one is actually the, what is called dilatation, or free dilatation of mu d, which means that this is the measure with free cumulants as the one are proportional to those of mu d, but dilated by a factor, I forget, L or 1 over L. Okay. claim is that we consider LH, which is conjugated by the diagonal with H diagonal. So if you take H quadratic function on the interval, you will get the reduced matrices. We look at as the primitive of the resolvent.
H.
Is the diagonal matrices, any. You see, for example, if n belongs to that, I think MH belongs to the subset, so we could have taken it. So there is some stability, trivial stability of the axiom also when you multiply them. Diagonal matrices. So if we know how to compute that, we know the spectrum, because the derivative is the resolvent. And the claim is that this is equal to, so the claim is this is the F dh is the extremum over A and B. You will recognize the large deviation function for step by this square. So I will do a mistake. Integral over dx log of 1 plus h of x b of x minus x plus a of x b of x minus f0 of x. With f0 of a is the analog of what I want for the R measure, but now for structure matrices. So it's a sum over P bigger than 1 over P, d product over K, dxk, a xk times gn gp of x1. So when this is independent, it produces. So that's the extremum is two conditions. So that gives a solution. Then you have to solve. Of course, you have the equation, but you have to solve for it. But now this is which is the extremum condition. And then I will stop, or I can give a hint of the proofs if you want. An extremum. I take the derivative. I put extremum because everything is formatted in. There is no z. Z should be here. Sorry. Let me check. I have the correct sign, I think. So the solution which are at the extra, so everything is in format series of z as usual. It's a moment method. So if I take the derivative with respect to b, I have something like ax is h of x minus z minus h of x dx. And if I take the derivative with respect to L, I have P of x, which is the derivative of f0. So this key. And then you can solve by recursion and so on. So if you know a bit about free probability, this is like more or less the air transform, but in a local way. And then now it's just an analytical problem to solve for this equation. So. Okay, so the way we prove it, so there is we get three different proofs. The first two are more or less the same. We use non-crossing partition are easy to deal with because there is a structure behind non-crossing partition. So that's what we use. That's why you get the implicit relation. And another one is to use tools which are in the book of free probability, which is related to what people call expectation value with accumulation, which in terms of usual probability theory is just a condition expectation value. So when you have a non-abelian algebra, you can take a sub-algebra on condition on the sub-algebra. You have to view this algebra as function. So here we could look at the algebra of matrices on condition on diagonal matrices. And this leads to this proof, and this is what I was doing when I was doing the trace of M with insertion of D. That's the way to deal with the condition expectation value in a hidden way. So the proof is that when we want to compute this kind of things, so this function, if we expand, we will have to, so you expand just the interval. So if you expand in Z, so the log Z may be plus, and I will be mistake with the coefficient, we will have Z to the 1 minus Z. And then we, instead of taking the trace, but we so I will so we look now at this, so we can write that integral of dx, but we take the matrix element of that. And that will be something like log Z maybe plus the matrix element, which will lead to n bigger than 1 minus n x and h trace of and h to the power n x. Okay, so that's something. These objects are a loop with endpoints, but with a mark point. Okay, and this one can be written as a sum over pi, where something depends on g pi. Okay, and then we invert the sum, then it means that we do the sum over pi and with an arbitrary number of points, but they are controlled by z. Okay, and then you can order the sum in two steps. You look at the partition in pi, which is associated to x. So, okay. So for example, you can order by which color I choose. Okay. So for example, you look at partition which contain x, the dual one. So that's some partition. So there is px into p star. When you organize the sum by the cardinal of the number of points in px, and if px is here, it means that you have some point here, and then you have to sum over everything which is here, which is of this kind, but without a contraction of x inside, because otherwise it would be. So here you reproduce the same sum many times. And then you have a factor which comes from this loop, which is one single loop, and this gives you the relation. And b of x, this gives you gx, x, no, this gives you the relation. And b of x is the sum, but where there is no x inside. And then you look, b of x would be the same, so b of x is something like that, but you should have it's a little one, so you have x here. And now it should be a singlet with respect to the dual partition. If you just look at these blocks, so here I have something like that. Now the same thing. This factor, this is on edges, so it will produce the factor, the loop of order n, gn, and then you have to sum of everything which is here, which can produce n, and that's this formula. So you really have this tree structure in the non-crossing partitions where you can deal with. Okay, I think it's probably there is things can be improved, maybe check. Maybe the good. So for example, I think the proof that we have for the stability of under non-polynomial transformation can be improved. For example, I think a good question is you take two matrices, M and M prime, and you look at what is the coupling between M and M prime, such as the product belong in the same set. Then if I think the proof, since it's more abstract and structure, it will be simpler, and this will imply the thing. Okay.
Conceptual question. So the original thing you showed with SUN variance, logical. Can I think of that as a random matrix with totally varying type of a SUN? I mean,
Yeah, this is what. So this structure also is present in ETH, what Jorge Nora did. The only difference in ETH is that you have a density which varies along the line. And locally, you say that locally you have a SUN. But it's very difficult to make sense of the concept of locally you have UN invariance, because maybe you have to extend it in some more abstract algebra. Because if you say that you have a UN invariance for, so you have a big matrix, to make it proper would be, I think, a good step in formulating ETH correctly. To have these big matrices, and you would like to have invariant, local invariance, UN. Therefore, for N, much smaller than okay?
mesoscopic.
Huh?
Mesoscopic.
Yeah, mesoscopic. But then when you do product of such a matrix, it becomes bigger and bigger.
Mm.
Okay, so you are.
Yeah, it's a good.
You have to give meaning to that kind
But that would be the idea.
Yeah, is that what you need for ETH? Yeah. But yeah, we just properly. Yeah. In a way, that is the same thing in QSEP. QSEP is the model for mesoscopic system. And even the node that we have in QSEP, we view it as emerging from low degrees of freedom. So QSEP, the vertices in QSEP is supposed to represent a fluid cell that you like, and with all the dynamic inside, which is supposed to be ergodic within the cell, but that is okay during some time at least. And so, and this is I in QSEP, or here it's just represents these small cells over which you expect to have the UN. So you should mix the two. It's very, very exact.
Yeah, the question. So you see there's a tree structure for this is integrated to this tree structure that one finds in the thermodynamic background. No one can derive TBA by matrix tree theory.
I don't.
Wait, so the way in which you're getting this F2 formula at the end, is
Sure.
the way in which you're getting this F2 formula at the end, you're not actually getting it as an extremum, you're getting it kind of from the formula you had on the right and then
No, we get it from that. And but these things is yeah.
And then you just reinterpret it at the last step, you
Exactly.
reinterpret
So
it.
we get the two extreme conditions.
Yeah, and then you just realize that this was.
Exactly.
Oh, I see.
Yeah. So we introduce this object, we introduce the object, which I call no, where there is no X in it, which is more or less B, this is more or less A, and we get it. You see, what is surprising that this formula, if you up to details, is the same thing as the large deviation for sets. Okay, which I mentioned, a new expression. But the large in SEP, in classical SEP, but in classical SEP, so this F is more or less the same thing as sum over J. Not PG to J in SEP. That's the random one. So this is more or less zero. Okay. But this is the practical problem. And these are Bernoulli variables, the same thing as protocol K. But this is just Bernoulli variable. And you can do the combinatorics. We did it with Philippe Bian, because we know the cumulants. And from that, you have to find the problem of finding you know the cumulant for the loop, for non-coincident indices, and you have to find the cumulant with all possible indices, including coincidence. So there is a long combinatoric. So this means that this combinatorics is coded by the same formula here. So during a long time, we didn't understand why there was this coincidence between something which is just classical probability, Bernoulli, and this is related to other problems for matrices. And now we understand it's due to the self-averaging property that I mentioned.
Self-averaging property for polynomials.
Yeah. Because you it's format series. That's a polynomial. Right?
Yes.
A long polynomial. It's a long polynomial. Everything is format.
Yeah.
So this means that this function is self-averaging.
Yes.
Yes. And this, you write it as expectation value of the determinant using the corresponding to set.
Yes.
So this function is actually, so expectation value of the determinant is expression of exponential trace log of the determinant, self-averaging, so it becomes useful. That's what the concept.
Any information on the eigenvalues of these matrices at some microscopic scale?
So Tracy.
Well, I mean, or even Wigner-Dyson statistics, or I mean, level repulsion. Is there any?
One function, this kind of thing.
I mean,
Yeah, maybe. I don't know.
sense to ask a question.
Yeah. You can ask questions for that. I don't know how to do it. I didn't do it. We did. You know, as much as I know. we just needed this spectrum of these matrices we want
This
to
is
compute.
just macroscopic scale.
Hmm?
There is no information. Microscopic.
But what? Yeah, okay. So maybe you have to add information because we just look at the leading term in the loop. So I don't know. But I am sure that there is some structure in the subleading term too, because maybe it's a bit as you said, the subleading in the first moment is linked to the second one. So we have seen many coincidences between these expectations, the subleading term and the moment of higher loops. There is many coincidences. So there is probably a structure behind that, which we didn't yet if at least you can impose some structure. So it's a bit open.